In today's lesson, we're going to be looking at linear combinations of matrices. Please be sure to subscribe so you don't miss out on any future videos. A matrix A is a linear combination of matrices B1, B2 up to Bk if there are scalars C1, C2, C3 up to Ck such that this following equation is satisfied. Note, the scalars C1, C2, C3 up to Ck are the coefficients of the linear combinations, and matrices B1, B2, B3 up to Bk must be of the same size. Let's look at an example. We want to determine if matrix B is a linear combination of matrix A1 and A2. In order to determine that if B is a linear combination of A1 and A2, we must satisfy this equation. Here, B is equal to C1, the coefficient C1, times matrix A1 plus the coefficient C2 times matrix A2. We can see in order to compute this right-hand side, we need to perform scalar multiplication twice. And we can see that C1 times 1 is equal to C1. C1 times 2 is equal to 2 times C1. C1 times negative 1 is equal to negative C1, and C1 times 1 is equal to C1. And we can use a similar approach here. Please watch a previous video on scalar multiplication and matrix addition to see this process in depth. Now that we have computed this left-hand side, we can see that we need to add these two matrices together. Next, we need to perform matrix addition to compute the right-hand side. But we must remember that in order to add these two matrices together, they must be of the same size. Since matrix A1 and matrix A2 are the same size, we can perform this operation. By adding this value and this value, we get C1. By adding this value and this value, we get 2C1 plus C2. And adding these two values, we get negative C1 plus 2C2. And lastly, adding these two values, we get C1 plus C2. We could obtain four linear equations by using the definition of matrix equality, where C1 is equal to 2, 2C1 plus C2 is equal to 5, negative C1 plus 2C2 is equal to 0, and C1 plus C2 is equal to 3. And by doing this, we can obtain four linear equations from this right here. Next, we need to write these linear equations into the augmented matrix notation. And we want to do this because we want to solve for coefficients C1 and C2. Next, we need to use the Gauss-Jordan elimination method to transform the matrix into reduced row echelon form. And we want to do this because we want to solve for the coefficients C1 and C2 to determine if B is a linear combination of matrix A1 and A2. Please watch previous videos on Gauss-Jordan elimination method and reduced row echelon form for an in-depth explanation, and the links to the video are in the description. A matrix is in a reduced row echelon form if the leading entry in each non-zero row is a 1 and all elements above and below the leading entry are 0. In this example, if we look at row 1, we can see that we have a 1 as the leading entry in this non-zero row. Therefore, we must satisfy the second requirement where all elements above and below the leading entry must be 0. In order to do this, we need to add a multiple of a row to another row. This operation leads to the matrix to the right, where we have a leading entry and all elements below this leading entry are 0. Next, we're going to analyze row 2. we can see that the leading entry in this non-zero row is equal to 1, so the first requirement is satisfied. And now we must use elementary row operations to ensure that all elements above and below this leading entry are equal to 0. And in order to do this, we are again going to add a multiple of one row to another row. And this operation is going to lead to this matrix over here. And here we can see that we have a direct solution where C1 is equal to 2 and C2 is equal to 1. Therefore, B is equal to 2 times A1 plus A2. And B is a linear combination of matrices A1 and A2. Thank you for watching. Please like, share, and subscribe.